Okay, perfect. So first of all, welcome everyone. This talk is about AI's environmental storage problem and how Storj has pioneered an architecture that can help reduce carbon footprint by up to 90%. So let's get into it. So the agenda for today, we're going to talk a little bit about Storj, DCS, the distributed cloud storage system, just the basics, so you kind of know a little bit about the network and how it works. We're going to talk about the costs associated with AI's transformative explosion and the huge data need that's created, in particular for cloud storage vendors. We're going to talk about how the architecture that Storj utilizes can help cutting carbon costs. And then we're going to take a couple look at some case studies if we have time at the end, just to see kind of a real life use case of how storage can be used in an AI workload. And then, of course, at the end, we'll have time for questions. Okay, so my name is Damein Morgan. I'm a senior software engineer at Storj. I've been working at Storj now for a little over 2 years. Prior to working at Storj, I was in the DoD world. So I worked at Lockheed Martin. Yes, I did work on the F-35 program. No, I did not write any code to make the jets play hide and seek with their pilots. Yeah, they did find that jet eventually, in case anyone was curious. But I was there for a couple of years, and also worked at Northrop Grumman for a few years as well. And then my background, graduated from Fresno State, computer engineering degree, and a master's from UCSD, also in computer engineering. Okay, so let's get started. So high level, the storage network has three main components, right? The application, storage nodes, and satellites. And the entire system is kind of similar to a supply and demand ecosystem. So before I get too far in, I'm curious, who here has actually heard of Storj before deciding to come to this talk? Okay, a couple folks. For either of you, have you used the Storj network before at all, or just kind of heard and knew about it? It's okay, you don't have to say. Yeah, it's okay. So a few people, that's cool. And for the rest of you, I'm excited to kind of give you a little bit of an overview of how it works, because it's quite a bit different, I think, than a lot of other cloud storage providers. So back to it anyways. Like I said, the whole system is similar to like a supply and demand ecosystem. So on the supply side, you have storage nodes that are run by individual storage node operators. Now, these node operators are not Storj employees, and we don't own the hardware that they run. They are individuals who have spare capacity on their hard drives and want to rent out the use of that capacity, as well as any associated bandwidth required to store and retrieve the data. Now, the hardware that these node operators run varies wildly, but it can range anywhere from a Raspberry Pi with an external hard drive attached, all the way up to a full-on data center VM. And so on the demand side, you have customer applications, right, who want to store data. So the applications interact with the network in actually a few different ways, but at the basic level, they're either storing data onto the network or retrieving data from the network. And they do this in a few different ways. They can utilize our native API bindings that we have for various programming languages. They can also use the uplink CLI tool for people who prefer a more command line style interface. We also have our hosted S3 gateway for those who prefer the S3 tools and API. And then we also have a web file browser for people who prefer a more drag and drop GUI kind of approach to storing and retrieving data. And so I should take a note here to mention that given the nature of our network and how the nodes are not run by us, we make sure to encrypt all of the data. So that's very important. And not a single piece of data stored on our network is unencrypted, right? We encrypt everything. That's important for us as a company. It's important for the customers and the privacy of the data. And it's also important for the node operators for various reasons. And so in between the supply and demand side, the applications and the storage nodes, you have what we call the satellite. So the satellite has quite a few roles, not least of which it has the job of maintaining all of the metadata that determines where all of the data is stored throughout the network. But in addition to that, it manages things like customer activities. So for creating user accounts and things like that, it keeps track of usage for things like billing and invoicing of the customer's applications. as well as the usage on the storage node side, right, for paying the storage node operators for providing the capacity to the network. And of course, also because it keeps track of all of the metadata of where the pieces are, it also facilitates some communication between the application and the nodes in some instances. Okay, so now that we kind of have a high level of what the components of the network are, let's take a look at a day in the life of the file. What happens when you upload data to the network and download it from the network? So as I mentioned before, the first step is encryption, right? Again, the encryption step is critical to the privacy of the data and the security of the network. And so right after the data is encrypted, the next thing we do is split it. And I'm going to deep dive a little bit into the split step because there's actually a couple of different ways the data is split. So let's just look at that a little bit closer. Okay, so once the data comes in, the object or file, it's split into something we call segments. So segments have a max size of about 64 megabytes. And for each individual segment, we then encrypt the data into something we call stripes. So the stripes are important because the stripes are actually themselves individually decryptable and requestable. So using an offset field, you can request just an individual stripe or a range of stripes for things like supporting seeking in a video, for example. Okay, so once the data is split and encrypted into the stripes, we employ something called Reed-Solomon erasure coding, which I'm sure a lot of you are probably already familiar with. I'm not going to talk too much about it, but let's just say that it's an efficient way to split data across several nodes while still providing the ability to reconstruct the data and adding high amounts of data resiliency. So once the data is actually split into the erasure shares, right, each stripe is split into it. I should mention we use 8029 Reed-Solomon, which basically means that each stripe is split into 80 erasure shares, and you need 29 of any of those erasure shares to reconstruct the original stripe again. And so you can see from the diagram here, let's see if I can point to it, the stripes are really just broken into these 80 erasure shares. And a piece, which the piece is what we call the component, the single smallest component that each individual node will hold, is really just a concatenation of those erasure shares with the same offset. So for example, if I wanted to request just this middle segment, and I knew that it was the offset of 1 on this piece, on all of these pieces here, I could request all of the pieces from these particular nodes with an offset value of 1 to get this first stripe. And that's essentially it, right? The data is split in this way, and once we have all of the pieces, then it's ready to be distributed across the network. So the distribute step, once the data is split, as I mentioned, the client application will then request a list of nodes from the satellite to store this data onto. And so as I mentioned before, we end up with 80 pieces per stripe, but it turns out that the satellite will actually return more than 80 nodes for the client application to store the data onto. And the reason for this is because the client can upload to all of the nodes that are returned and simply store the data on the fastest 80 nodes to upload the data. And then it can cancel the upload for the remaining nodes, such that you basically get the fastest of the bunch, essentially. Okay, so that's great. Now the data is stored securely in the network. It's encoded, it's encrypted, but how do we retrieve it? So this is essentially just the reverse of the upload step. So first, the application will communicate and authenticate with the satellite to get a list of nodes to download the data from. As I mentioned, only 29 nodes need to provide a piece to reconstruct the original data. But again, the satellite will return a list of more than 29 nodes. And the client can then download from all of those nodes in parallel. And the fastest 29 are the ones that win the race, essentially. And those are the ones that the client uses to reconstruct. And the remaining downloads are just canceled. And so once the pieces are downloaded from all the nodes, Reconstitution of the segments is just the reverse of that erasure coding step that we talked about earlier, right? Taking all the erasure shares and converting them back into the segments. Then you decrypt those segments, which gives you one or more segments that can be used to either reconstruct the full segment or reconstruct the full file if that was requested. Okay, so now that you kind of have a high level of how the network works, let's shift gears a little bit and talk about AI's transformative explosion, the huge data need that is on the back of the explosion in AI demand, as well as a little bit about the AI workflow and where cloud storage vendors fit into that workflow. Okay, so statistics vary depending on who you ask, but Statista says that by 2025, the world will be at 181 zettabytes worldwide. So for anyone who doesn't know, zettabyte is 1 billion terabytes. So that's 181 billion terabytes of data. And that's the data, that's everything, right? That's the data generated, that's the data consumed, copied, captured, that's everything. So Statista made this chart, and it turns out that the 2021 through 2025 data is actually based on, is actually an estimate based on the data that was in 2020. So this likely doesn't even take into account the huge acceleration of data that's been generated over the past couple of years due to the explosion of AI workloads. So Cybersecurity Ventures, another company interested in research and reporting, says that the Statista chart is an underestimate and that the real amount of data to be generated in 2025 is actually over 200 zettabytes. So we've got to add some more CDs to the chart here. Maybe we'll end up at Mars before Musk does, who knows? But in any case, it's a huge amount of data, right? No matter how you slice it, the world has to do something to account for this huge explosion in data. And it makes sense, right? So Cybersecurity Ventures also estimated that not only is the amount of data generated going to be over 200 zettabytes, but also that 50% of all of the data stored will be stored in the cloud, which is up from 25% in 2015. So, I mean, and that makes sense considering how easy it is now to use cloud storage, right? In some cases, mounting it to your local machine can be indistinguishable from local storage. But the point I'm trying to make here is that the huge amount of data that's being generated and this acceleration of it through 2025 is already on the backs of this shift of pushing data into the cloud, creating a huge need for capacity in cloud storage that needs to be addressed. And so now that we know the need is there, let's take a look at AI's specific needs around this data. Okay, so the generative AI lifecycle, generative AI workflow has three main phases: model creation, model customization and fine-tuning, and model execution or model inference. So each of these phases, to varying degrees, has a need for transferring data sets from cloud repositories to some training environment. And the training environments can vary, and the data sets and the models are typically transferred between environments in some cases, across geographical regions and things like that. And then ultimately, during model execution, any output produced from the execution and inference phase is shared either over a private network or the public internet. So it's probably no surprise to anyone who's paid attention to the AI industry over the past few years, but the number of AI data sets is growing exponentially, right? And not only that, but the size of the data sets and the models themselves is also increasing rapidly, just due to the huge demand for AI these days. So in this chart, we've highlighted the storage components as blue, the compute steps as red, and the green in the arrows here represents data in transit. Okay, so the question remains, where do cloud storage vendors fit in here? Well, in some cases, cloud storage vendors can be used for the data at rest, depending on the performance needs of the the AI workflow. So at Storj, we actually don't offer any compute resources. Nothing we can do about that, but a lot of cloud storage vendors do, right? So there's certainly some work to be done there as well for those cloud vendors who do offer compute. But what about the green here, right? So it's probably no surprise to anyone in this room, but it's not good enough typically to just store the data somewhere. You have to have a way of getting the data where it needs to go. And that needs to be done quickly, efficiently, economically, right? Cost has to be considered, but not just the monetary costs, the carbon costs, right, must also be considered. Like how much, what's the carbon cost for transferring these AI data sets and models around the world to be used in different AI data workflows? So unfortunately, like I mentioned, we can't help with the compute, but it turns out that Storj's network architecture is can help with the green and the data transit. So let's find out why. So cutting costs with carbon. So before you can decide to cut carbon, right, you have to really define what the real carbon generation is, right? And so that's what we're going to look at. How much carbon does it take to store and distribute all of the data, the AI data models and the data sets around the world? Or how much carbon does it cost to create and ship drives for long-term storage and CDNs all around the world? So let's look at that a little bit more closely. So, of course, when people think of the carbon costs associated with these types of workflows, the first thing that comes to most people's minds is data centers, right? Just how much carbon are data centers actually creating? Well, it turns out when it comes to data centers, one of the biggest factors, as you've probably, if you didn't already know, learned from the previous presentations that we've seen today, is just building the data center, right? So shipping the raw materials that make up the data center, right? The concrete, the wood, the sheet metal, et cetera, shipping that all around the world. This is all sometimes called embodied carbon, and it includes the logistics of all of that, as well as shipping servers and hard drives and all of the components that go into the data center around the world. So the thing about this embodied carbon, right, is that typically these costs are paid before the data center is even turned on, right? So you're not even really getting any use out of the data center yet, but you already have this cost paid. In addition to the embodied carbon that I mentioned before, there's also the electricity, right, which is what's shown on the screen. So obviously the big users of electricity in the data centers are the servers and the cooling and power systems. But it turns out the storage drives and the network themselves take up a decent chunk, right? 14%. That's not a small amount. And so that's really what the storage architecture is meant to help with, given that we don't have any compute resources. Another couple of things that typically fly under the radar when you talk about data center costs in terms of carbon is the chemicals that are used to cool the data centers, right? The disposal of those chemicals is terrible for the environment. And also the minerals, right, that go into some of the components that are used, for example, the battery backups that back up the data center facilities. Okay, so don't get me wrong, the world is always going to have a need for data centers, right? That need's not going anywhere. And in some cases, especially the hyperscalers, right, it makes sense to amortize these costs via other means. Doing things like buying carbon offsets for the compute workloads, or building data centers close to renewable, clean energy sources, and things like that definitely go a long way to help this need. But it's not always manageable, right? Like tier 2 data centers, corporate data centers, those kinds of things typically sometimes don't have the efficiencies that are needed to really offset these costs. And so that's where a network like Storj comes in, right? We don't buy hard drives the same way Airbnb doesn't buy houses to add to the capacity of their service, right? We don't build data centers to build out, to store hard drives to build out our capacity the same way Airbnb doesn't buy hotels, right? Or build hotels. We write software that allows other people, our storage node operators, to utilize their existing hardware to add capacity to the network, right? Their existing hardware and the infrastructure as well. And so beyond that, the Reed-Solomon coding scheme that we employ has an expansion factor of just 2.7. And with that 2.7, we're able to get consistently great worldwide performance without the need for building tons of data centers, right? Or another way of saying it, we don't have to build data centers at the edge to then duplicate data, right, to the drives that are stored in those data centers to get content to the edge, because on our network, the data is stored on the edge. So what about the drives themselves? So let's talk about that for a second. So the carbon cost of a hard drive is tricky to accurately define because it has several factors. And again, if you've seen the presentations earlier today, it's probably no surprise to you that one of the biggest factors is the manufacturing phase, right? So 62% for the raw materials, 11% for the assembly. This, by the way, is a 1 terabyte Seagate Momentous drive. And then not only do you have the phases of the manufacturing, but you also have the logistics and transport of the raw materials and components around the world, right? You also have the lifetime of the drive, so the product use, how long is the drive in use for, and the disposal technique, or if the drive is even recycled at all, right? That can also factor in. So researchers published a paper on embodied carbons and SSDs. They performed the life cycle assessment of 26 drives of various manufacturers and sizes and determined that the manufacture of 1 terabyte of hard drive capacity resulted in 20 kilograms of CO2 produced. They further found that powering that drive over a 5-year lifespan resulted in another approximately 80 kilograms of carbon. So why did they use 5 years? Well, the study itself actually has results for both a 5-year and a 10-year lifespan, but it turns out most drives are taken offline after only 3 to 5 years. And there's several reasons for that, but one of the big ones being the drive warranties, right? The warranties only last 3 to 5 years. So it's not surprising that a storage provider using traditional methods would not want to store important data on out of warranty drives. It's just too risky. So now that we have some concrete numbers for the manufacture of the drive, I want to kind of do a thought experiment here to wrap our heads around just how much carbon is that, right? So one of the charts we showed before, let's take just the difference in the amount of data generated between 2023 and 2024, right? So from 2023 to 2024, that's, let's say, 25 zettabytes or so. So again, 25 billion terabytes, right? And we just learned that to manufacture the drive is 20 kilograms of CO2. And to power it for 1 year, if I take that 80 and divide it over the 5 years, that's another 16 per year. So that's 36 kilograms of CO2 for a 1 terabyte drive to power it for the year. If we multiply that by the 25 billion terabytes of data need, that's 900 billion kilograms of carbon, or 900 million metric tons of carbon. So for context, that's just under what the entirety of the aviation industry produced in 2019, right? So obviously 25 zettabytes is a huge amount of capacity. I don't think that anyone is producing that in a year, but I don't think it would be too long before we potentially reach that if we continue in the direction that we're headed now. So how can Storj's architecture help with that? Well, we can't make it any cheaper to produce, in terms of CO2, to produce a drive yet, but if there's any manufacturers of drives out there and you use cloud storage as a part of your manufacturing process, come talk to us, because maybe we can. But what we can do today, right, is reduce the need for new drives by allowing people to use their excess capacity, right? Not only just increasing the usage of the drives, but also increasing the longevity of the drives. It turns out that our network is well suited for a lot of these older and out of warranty drives because of the erasure coding scheme that we employ that only requires 29 out of those 80 pieces. And I'll talk a little bit more about that later, but if this sounds familiar, it's the same story of how this type of architecture can reduce the need for as many data centers as well. Okay, So I've made some bold statements up here about reducing the need for drives and things like that. So let's take a little bit of closer look at those claims. At the end of the day, those 200 zettabytes of data, right, that are going to be generated in 2025 need to be stored somewhere. And we're not magicians just storing bits of data into thin air, right? The Airbnb approach to cloud storage is cool and all, but we still require our node operators to have hard drives. So don't we just push the carbon cost onto them? Well, the answer is it depends. If node operators go out and buy brand new hardware just for the purposes of running a storage node, then the carbon cost is the same, right? Albeit slightly lower due to the absence of a data center. But if operators use their existing hardware, then there's no increase in carbon costs resulting from the manufacture of a new drive, and only a slight increase in carbon costs associated with operating the drive at a higher capacity. And so the real question is, how much unused capacity is out there, already being powered, already being cooled, that can be utilized for our network? So smarter people than me looked at this question, and according to NRDC and IBM, most servers operate at only 12 to 18% capacity. That number is from a few years ago, but and I hope that it's gone up since then, but it still implies that there's a huge reservoir of already powered, already cooled drives that are just severely underutilized. So we were curious about this in our network as well, so we decided to survey our node operators. So on our network, it turns out that 21% of our capacity is coming from node operators that already had their drives in use for some other purpose, right? And so as I mentioned, in those cases, there's no extra carbon paid for the manufacturer and only slight increase in carbon paid for running the drive at higher capacity. It turns out another 21% of our network is provided by another 21% of the capacity is provided by node operators who brought old hard drives back online specifically for the use or for the purpose of becoming a storage node. And in those cases, there's also no carbon costs associated with a new drive and just the cost associated with now running a drive that was not operational. So that's over 40% of the capacity in our network that has no cost associated with manufacturing of a drive, which, as we learned earlier, is a huge cost portion of the cost. So as I mentioned earlier, those old drives are likely more prone to failure than newer drives or drives that have been in service for a little while. But Storj's network is a bit unique. So we have something in our network that we call node churn, which is basically when a node operator decides to leave or join the network. And so given that we have to deal with nodes potentially vanishing from the network at any given time, we had to employ a much higher assumed rate of failure in our network than typical cloud storage providers have had to do. So it turns out because of that factor, things like older hard drives being used that die and go offline has almost no impact on the durability of our data. And so in addition to that, we also constantly monitor the network to look for not only storage nodes that have gone offline, but also malicious nodes, right? Things like that, because it's an untrusted network. So we're constantly surveying to make sure that the data is reliable and durable. And if we see that the piece counts are getting too low, we'll immediately repair that data onto different nodes. So while we can't make the drives themselves last longer, drives do have a finite lifespan. What the architecture can do is squeeze every inch of life out of those existing drives to help reduce the amount of carbon overall. Okay, so at this point, everyone is saying, yay, storage, go storage, I'm gonna use storage, right? But there's gotta be a catch, right? So what's the catch? Is it slow? Is it difficult to integrate into your workloads? So let's take a look at a couple of use case examples to see just how it performs and its uses. Okay, so first up is the Lown 5B dataset, which is a dataset training dataset used for research purposes that consists of 5.8 billion clip filtered image text pairs. So think like an image with a caption, right? And so This is an example of the first phase of the AI lifecycle, where an AI is trained using billions of data points, and ultimately a model is produced that gets passed on to the next phase of the lifecycle. So for this test, we narrowed the scope a bit to just the English language samples, which consisted of about 2.2 billion pairs. And we uploaded the data to both an AWS S3 bucket as well as a Storj bucket. So on Storj, the 2.2 billion pairs took up about 3.5 terabytes of space. That's after the 2.7 expansion that I talked about earlier. And then we focused in on just the first 10 1.4 gigabyte image embedding files. And one of those image embedding files is what you see on the screen here. Each of those dots represents a storage node somewhere in the world that's storing a piece of that data. And there's 1,760 encrypted erasure encoded pieces for one of those image embedding files. It's worth mentioning that, and so as a part of this test, essentially what we did is we tested downloading this data from different locations around the world. And it's important to note that these are relatively large files, probably close to the limits of most object delivery for CDNs. Okay, so what was the result? So this chart's probably a little hard to read. Sorry for it being so small, but the y-axis here represents the mean time to download, so lower is better. And each grouping represents one of the download cases. So the colors here, each color represents a different location that we downloaded the data from. So blue here is Amsterdam, orange is Bangalore, green is Frankfurt, red is New York City, purple is San Francisco, brown is Sydney, and pink is Toronto. So as you can see from the chart, the S3 accelerated download speeds perform the best. But on the right there, the Storj DCS Global, that's our native API, and the Storj Linkshare Global, which represents our S3 gateway, had faster speeds than the AWS West standard download, except for the purple there in San Francisco. So what's the case with that? What happened there? Well, it turns out that the upload in AWS was actually to the US West region of AWS. And so the San Francisco download happened to be in close proximity to the US West AWS bucket. And so this goes, I mean, common sense, right? Like the data is closer to you, of course, it's going to be faster to download. But the cool thing about this common sense argument is that it means, you know, older, slower hardware can still give you high amounts of performance when the data is right next to you, right? A Raspberry Pi with an external hard drive may not be a great fit for a high-speed workload in a data center, but when all you need is one piece out of 29 pieces from that Raspberry Pi and it's right next door to you, that changes the equation a bit. So taking this argument a little bit further, the chart on the right basically shows the mean time to download versus the proximity to the AWS West location. And as you can see, the AWS standard offering, you know, the further you get from that US West, the slower the download. But Storj has a much more consistent global download speed because of the fact that the data is already split and stored around the world. So let's take a look at another example. This is the Storj. This is actually an example of the third phase of the lifecycle, which is the distribution of the model for data execution. So for this test, we downloaded the star coder model from Hugging Face. So if you're familiar with Hugging Face or not familiar with Hugging Face, it's a repository that can be used to share AI data models. And so we downloaded this particular data model. It's relatively large at 64 gigabytes. And downloading it from the Hugging Face Hub library took about, gave us a speed of about 75.8 megabytes per second. So it's worth noting that Hugging Face uses a CloudFront CDN, but the CDN was not hydrated. The cache was not hydrated for this download. And so we took that same data and we uploaded it to Storj and mirrored the same bucket structure as the Hugging Face Hub bucket, the AWS bucket that they used. We updated we deleted the local application cache and then just updated the metadata to point to Storj using the S3 credentials. And we set up a parallel download of 16 connections. And with that change, the download speed was up to 212.7 megabytes per second, which is about a 3 times improvement. And so it's important to note here with this test just how well the Storj network architecture adapts to concurrency, right? So given that you're downloading from several nodes across the world, it's a lot easier to add parallel connections to each of these nodes, and typically is only limited by the resources of the machine that you're using to download from. And so downloading in parallel with the Storj API is as simple as just adding a dash parallelism flag, and you'll then be downloading those segments in parallel. So this Hugging Face Hub library, we created a monkey patch for it, and you can find that on GitHub. So if you use Hugging Face to distribute your models, go ahead and give it a try. Okay, so let's now tie it all together. What are you really getting with a network like Storj? Well, basically what you see on the screen here, right? Multi-region by default, high amounts of performance, high amounts of availability, 11 nines of durability, privacy, encryption, and the price, of course, speaks for itself, right? Much cheaper than most other cloud vendors, cloud storage vendors, and maybe even the cheapest one that I've seen. But what do you get really when you peel back, this kind of surface layer look at what the service offers and really look at what the architecture can give you, right? How can you really achieve that 90% figure that we talked about in terms of your carbon cost savings? Well, it comes down to just a few simple things, right? Having nodes with efficient use of distributed capacity, right? So utilizing existing hardware and existing infrastructure to reduce the costs associated with having to build out that architecture, to build out that the data centers and the hard drives, it is one big component. But in addition to that, like I mentioned, increasing the lifespan of the drives, right? Bringing those old drives back to life to use on a network like this that has a high amount of redundancy and resiliency baked in can go a long way to cutting the costs as well. Beyond that, the erasure encoding scheme that I mentioned has an expansion factor of just 2.7, like I said. And with that, it's a relatively low amount of data duplication that can still provide you global performance that is, in some cases, can rival CDNs. On the point of CDNs, typically a lot of CDNs will employ caching, right, using SSDs. It's a caching layer. And so the cost savings associated with using a network like Storj and not using a CDN can be huge, because it turns out that SSDs have anywhere from like a 2x to a 8x cost compared to traditional hard drives. So the absence of those is also a huge savings. And so how did we get to this concrete number? Well, it's impossible to measure the savings precisely, but using conservative estimates, and if you're curious, I encourage you to check out our sustainability white paper on our website. But we estimated that if you use a network like Storj, the same type of architecture, and you're using all 100% already powered hardware, that you'll save about 95.3% of your carbon when compared to hyperscalers, or 97.7% when compared to typical corporate data centers. For our current network in its current state, with, as I mentioned, 40% of our capacity, 40% of our capacity provided by node operators that are either reusing existing hardware or bringing old hardware back online again, the savings is about 65.6% compared to a typical hyperscaler, or 83.5% compared to a typical corporate data center. And I'll open it up for questions. Okay. Sorry, I thought I ran out of time. Questions? No, go ahead.
So Reed Solomon is notoriously computationally expensive.
Yes.
And if you did server-server direct comparison, fetching the data out of the cloud or your locally attached storage versus going out to your Reed Solomon facility, presumably you're putting a lot more load on your server. So your OpEx, both in dollars for direct energy costs and your carbon OpEx are going to be quite a bit higher.
Yep.
There are ways around that if you're using server CPUs from some of the manufacturers, but most of the CPUs that you're using sound like they're not server CPUs. Am I missing something?
So to repeat the question was, and please correct me if I got it wrong, but so we're employing Reed Solomon or Azure coding as a part of our network. And the question was, given that the Reed Solomon or Azure coding itself is fairly CPU intensive, and that we may or may not be using server CPUs as a part of that, have we factored in the increased carbon costs associated with that extra workload? Is that correct? Okay. And so it's a very good question. Again, I encourage you to check out our white paper on sustainability to get some more exact figures on what we considered when we came up with our numbers. But we treated, to answer the question, we treated all of the associated costs, all of the associated data center workloads. I should mention, so we're told by our service providers that all of the carbon costs associated with our data center use is offset, but that actually wasn't factored into the equation. So we did look at just how much resources are we using in the data centers for things like the satellite compute steps that are run as a part of the network. So that was factored in to that 65% that I mentioned, and is also factored into the full use of 100% of nodes as well. So the extra percentage that, 95%, so that extra 5% or so is associated with the costs of that. And I should also mention that a lot of the computations that are done for things like the encryption are all client side, right? And so the associated costs with those are often things that the clients themselves will have to deal with the increased usage of having to encrypt the data and things like that. So does that answer the question? Okay. Yep, another question.
So when you look at a system, you are actually, how to say, looking at $4 per terabyte per month. And I'm guessing since you showed this graph saying that your data is literally very quick, so that means that over there.
Yep.
So it's very quick and but now you can get a cold storage here from AWS for $1 per terabyte per month, where the time data is 24 hours, 48 hours. You look here, if there's more of a multi-tiered model or SMA that may be available, and another comment is you show the 1 terabyte. I don't think you can get 1 terabyte in graphics guys anymore. You are more like today, some customers have access to 50+ terabyte drives, so maybe you can offer them.
Yeah. Okay, so I'll repeat the question. Actually, there's two questions. So the first question is, do we offer, and correct me if I'm wrong, do we, a service like AWS has a cold storage tier that is cheaper than their typical offering. So the question was, do we have something similar, like a tiered approach that has a different price than our regular offering? And the second question is, sorry, can you? Oh, yeah. So I got it. So the second question was, I mentioned that the study on research and embodied carbon, they found the carbon cost of a 1 terabyte of capacity. So to answer the first question, as of right now, we have just our single tier offering. We feel that that's competitive at all levels, given that we don't have any restrictions on the data access, like a cold storage solution would. But I do know that we're always looking at new products, so I wouldn't be surprised if that's something that we offered in the future. And then for the second question, so the research paper on embodied carbon, as I mentioned, they looked at 26 different drives of various manufacturers and sizes. So I think the largest drive they looked at in the study, I want to say, was 6 terabytes. So they did look at larger drives when they came to that conclusion. Not as large as, you typically find today, like 18, 20, I've heard that we're coming on to 50 terabyte drive soon. But they did factor that into their life cycle assessment. Any other questions? Yeah. The 5,000 gigabits per second? Oh, the bandwidth price. Yeah, so that is egress bandwidth. Any other questions? Oh yeah. Oh yeah. Oh yeah. Bring them onto the network. Yeah. From a carbon standpoint, right? Any use case of bringing on old drives, right, will always provide capacity that reduces the need for manufacturing new drives to fill that same capacity. So again, as I mentioned, while we do pay a slight cost of you now having to spin up the drives and use the electricity for them, et cetera, we don't pay that huge cost of manufacturing those terabytes of capacity. So bring them on. We've got native storage node software that you can run on those drives on your NAS. We are Docker compatible, right? You can bring up your entire storage node as a Docker container, right? And the storage node themselves, the software is very minimal. It's basically just a file server. It's got like an embedded SQL database in it to keep track of where the pieces are on the nodes, but it's, doesn't take much to run, can run on very low hardware. As I mentioned, we have people running it on Raspberry Pis with external hard drives attached, right? And still delivering performance, right? Typically only to people who are downloading pieces from within their vicinity, but they're still getting high amounts of performance from those nodes. So yeah, absolutely. Oh, another question back there? Yep. 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 Right. Okay, I'm going to try my best to repeat the question. It's a great question, by the way. So the question was, that even if we use a solution like Storj or this type of an architecture, what happens if the demand for capacity outstrips all of the hard drives that we can actually install the storage nodes onto? Aren't we still back to square one? And the answer to that is yeah, we are, which is why it's important. If you were here for any of the other previous talks, some of the advancements that are going into, just making it a lot cheaper in terms of the carbon cost to actually produce storage media or different types of media, right? This is not necessarily to take away from any of that work, and that work is certainly still important. This is just more of trying to efficiently utilize the capacity that we do have, right? And so if every hard drive in the world that had spare capacity ran Storj, that'd be great. I would love that. But yeah, you're right. It would only take us so far because eventually we would need to start producing again to meet the capacity demands. All right, well, if there's no more questions, thank you.